All right, good morning, everyone. So last time we had been in the process of working out the energy eigenvalues and wave functions for hydrogen-like atoms. And so these are systems where you have a nucleus consisting of Z protons. Z is an integer in your nucleus. It's also got, in general, some number of neutrons, but we don't care because they don't have electric charge. And we're pretending that the mass is infinity, just so that the nucleus won't move. And then there's going to be one electron with mass that we're calling mu. Okay, and if you want, you can always just set Z equal to 1 to get real hydrogen. And we're interested in bound states. And what we found is that the energy scale associated with these things is the mass times the electric charge in our units that we're using to the 4th power divided by 2h bar squared. And that's a famous number known as 1 Rydberg. And it's equal to approximately 2.179 something 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 times 10 to the minus 18 joules, which is also known as an even more famous number of 13.606 something 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 electron volts. And then the energies of the bound states are labeled by an integer n, and they're just equal to minus z squared times a Rydberg, 13.6 electron volts, divided by n squared. Okay, and the integer n is equal to the sum of two other integers, k plus l. And it has to be one of the integers that's positive. And one of the reasons we know that is because when we worked out the differential equations, we found out that k was a positive integer. And L is the angular momentum quantum number. So on general grounds, we know that that's a non-negative integer. So we know those two things. So we know what the allowed n's are. And then corresponding to those energy eigenvalues, there are wave functions. And because we have spherical symmetry for this problem, we can sort the wave function into a radial part, which depends only on n and l, and it depends on a radial coordinate rho, times a spherical harmonic that always comes for angular momentum eigenstates. And we found out something about the r's, the capital R's, namely that they are a decaying exponential times a factor of rho to the nth power times a polynomial, which we wrote as a sum from j equals 0 to k minus 1. So k minus 1 is the order of this polynomial times some coefficients that we haven't worked out yet, but we know something about them, times rho to the jth power. So in this business, there's always these changes of variables that we do. And so rho was related to the original radial coordinate as r over a factor of b. B turns out to be n times h bar squared over z mu e squared. Okay, and so putting that together, rho is equal to z over n times the radial coordinate over something we can call a0, where a0 is equal to h bar squared over mu e squared, and that's known as the Bohr radius. of the hydrogen atom. And it's numerically about 5.29 something 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 times 10 to the minus 11 meters. Okay, but if z is not 1, then we know from these things how z scales into the problem. The energy scales like z squared, and the dimensionless radial coordinate scales like z, which means when z gets larger, then the atom is going to get smaller because that's inversely scaling with r. Okay, and so now we can draw a graph of the energy levels. For the bound state, the energies are negative, so I'm going to draw 0 here. And I'm just going to do this for hydrogen. So down here somewhere is negative 13.6 electron volts, negative 1 Rydberg. And we can label things by the different values of L. So there's an L equals 0 column. Okay, and in that column, there's n equals 1 here. And then n equals 2 is about a quarter of that. So that's n equals 2. And then there's n equals 3 up here somewhere. And then there's n equals 4. And they get closer and closer together, unlike the 3D harmonic oscillator where they stayed equally spaced. These ones get closer and closer together. And then we shouldn't forget that these were just the bound states. There are also up here a bunch of continuum states with energies above 0. So I could shade that in because those are continuous. They're not discrete lines. Okay, and so there's a bunch of states up there, which we didn't solve for, but they exist. And it's good to know that they exist. So that's for L equals 0. For L equals 1, for L equals 1, if we go back to this equation, now n is going to start at 2 because k starts at 1 and L is already 1. So that means we're at an energy level that's up here at n equals 2. Oops. Okay, and then the rest of the states are just increasing k. So they're all there. And once again, there's a whole bunch of continuum states here that are shaded because they're not discrete. And then if we go to L equals 2, now we're starting at n equals 3. So in each case, I'm labeling the lowest state. Once again, there are continuum ones, and so on. So for L equals 3, now we're starting at n equals 4. Okay, and so for a given value of n, L max is equal to n minus 1. So what that means is, let's say I start like at the n equals 2 level. If I follow this along at some point for each value of n, at some point I've run out of L's, and there beyond that over here, there are no energy levels. So there's a maximum value of L for each n, and that's what it is. It's n minus 1. We can also talk about the degeneracy. We're just counting states here. So for each L, we know that there are the following values of m, namely minus L plus 1 up to L. And so there are 2 L plus 1 of those. That's a general feature that's always true if you have rotational symmetry in quantum mechanics. Those are the allowed values for m. Okay, and so now the degeneracy for the energy level n is I sum over all the L's that can contribute, which is L equals 0 up to n minus 1. That's from here. And for each one, I sum over the degeneracy of that level of n and L, which is 2L plus 1. That's the sum of the first n odd integers, which is famously equal to n squared. Okay, so the degeneracy of the level of the energy level n is n squared, but actually this does not take into account spin. And spin contributes a factor of 2 for the electron. And it also contributes a factor of 2 if you have a proton. So when you're doing the counting, it just matters whether you're including those spins or not. If we're not including the spins, then it's just n squared. Okay, so there's always, whenever you're doing science, you always have to invent some code so that newbies can't easily understand what you're doing. And so there's the spectroscopic notation, which is our conspiratorial notation to make sure that you're not able to follow what's going on until you're initiated. And so when we're talking about L equals 0 states, those are called S states. That originally stood for sharp. And L equals 1 states are called P, which stood originally for principal. This has to do with the character of the spectroscopic lines and transitions among these states. For L equals 2, it's D. For originally, it was diffuse. And for L equals 3, we call those F for fundamental. And so you just have to know the code. And then for every larger value of L, it just goes alphabetically from there on. So it's G and H for L equals 5. And one usually doesn't talk too much about states with higher L than that. So, but it goes alphabetically from there on if you need to. So people will talk about, for example, the D wave. D wave just means it's a code that the orbital angular momentum is 2. If they talk about S wave, that's just code that says the orbital angular momentum is 0. Okay, so now let's go back to the radial coefficients. So if we go way back up here, we had these polynomials that appear. Oops. And so we need to know something about the coefficients. Unfortunately, last time we worked out a recursion relation for them. And that looked like the following. Okay, that the jth coefficient is equal to the j minus 1th coefficient times a factor of 2 times j minus k divided by j times j plus 2l plus 1. Okay, so as a check, if I plug in j equals k, that tells us that c sub k is equal to 0, which means the sum is terminating, which means it's not an infinite sum, it's a polynomial. And as is very common in problems like this, we found out that it had to be a polynomial because if it wasn't a polynomial, then the infinite series would sum up to an exponential and it would blow up at infinity, and that would not be an acceptable solution. Okay, so let's just take these coefficients and consider the smallest few polynomials that we can get, just for some examples. So the smallest few values of n, which is equal to k plus L. Okay, and whenever we pick an n, we're picking an energy level. So if we pick n equals 1, that's the ground state. And so if n equals 1 and we look at n equals k plus L, there's only one way to get that, because k can be 1 and L can be 0, and that's the only possibility. Right? So in that case, C1 is equal to 0, because k is equal to 1. But C0, by definition, could not be 0. And so our polynomial here is just a constant. And we're not going to worry right now about what that constant is, because later on, we're going to choose the constant in front of the whole thing in order to make the thing have unit norm, in order to make the wave function have unit norm. Right? So in this case, the polynomial is just a constant. For n equals 2, the first excited state. So now there are two possibilities. There's a possibility that L equals 0 and k is 2. Okay, and in that case, then C1 is equal to C0 times 2. We're just plugging into the recursion relation here. Okay, so C1 is C0 times 2 times 1 minus 2 over 1 times 1 plus 0 plus 1. Okay, which turns out to be just negative C0. And then C2 is 0 because k is 2. Right? So we always know the C sub k is 0. That's where the thing terminates. And so if you put that together, our polynomial as a function of rho, the rescaled radial coordinate, is 1 minus rho times a constant. And again, we're not going to worry right now about what that constant is. What's important is that it's proportional to 1 minus rho. Okay, but the other possibility for n equals 2 is that L can be 1, in which case k has to be 1. If k is 1, then that tells us immediately that C1 is 0. And so our polynomial for P21 of rho is equal to C0. I should say the subscripts here are n and L on each of these polynomials. So anyway, for that case, the polynomial is again just a constant. Now we can look at n equals 3, just to see how things go. So now there are three ways to get n equals 3. One way would be L equals 0 and k equals 3. Okay, then, first of all, we start with C0 and then we get C1 from it. So C1 is equal to C0 times plugging into the recursion relation. It's just arithmetic. 2 times 1 minus 3 divided by 1 times 1 plus 0 plus 1, which is negative 2C0. And then C sub 2 is equal to C1 times some fraction, which happens to be 2 times 2 minus 3 divided by 2 times 2 plus 0 plus 1, which works out to be minus C1 over 3, but we already know what C1 is, so this is 2C0 over 3. So everything gets written in terms of the first coefficient, and so in this case, our P30 polynomial is 1 minus 2 rho plus 2 rho squared over 3 times the overall normalizing constant, C0. Okay, and then if L equals 1, k equals 2, I don't think I'll go through the arithmetic this time in detail. I'll just write down the answer, which is the polynomial is equal to 1 minus rho over 2 times a constant. And then the last possibility for n equals 3 is L could be 2 and k could be 1. And then there's only one term. And so that was P32. this is just equal to some constant, C0. So one thing I should emphasize is that for each one of these polynomials, the C0 is actually a different number. They're not all the same C0. So all the C0s are arbitrary at this point because we haven't normalized things, and different. Okay, so for any value of k and L, and therefore any value of n, you can construct the polynomial, and you can ask what they are. What polynomials are these? And the answer is they are, again, associated Laguerre polynomials, the same class of functions that we found for the harmonic oscillator, for the 3D harmonic oscillator. Okay, so it turns out PNL of rho is an associated Laguerre polynomial. And that means it's proportional to, again, we haven't worried about the constant in front of these yet, the associated Laguerre polynomial with lower index n minus L minus 1 and upper index 2L plus 1. But it's the Laguerre polynomial of 2 rho, not rho, which is tricky. Okay? And another way of writing this is also known as L upper subscript 2L plus 1, lower subscript k minus 1. Okay, because k minus 1 is n minus L minus 1. With argument, if I just plug in for rho is, it's R over B, where B is the thing that we wrote down previously. Okay, so again, unfortunately, there are multiple conventions for the Laguerre polynomials. This is in my convention, which happens to be the same as Wolfram's. And one reason I like this is, again, that there's an explicit representation for what the associated Laguerre polynomials is. We wrote this down before, but I'll just write it down again for the record. So there's a formula you can just plug in, where you have to take n derivatives, n derivatives with respect to x, where n is the lower index, of e to the minus x, x to the n plus alpha, where alpha is the upper index. Okay, and so you compute that thing, and that's the associated Laguerre polynomial in my conventions. Okay, and n is an integer, and alpha need not be. It can be anything. In this case, it happens to be an integer, but for the 3D isotropic harmonic oscillator, it actually turned out it wasn't. So recall, for the 3D isotropic harmonic oscillator, the functions that came in there were L sub k with superscript L plus 1/2 of R squared over B squared. Okay, so first of all, its argument was not the radial coordinate, but the radial coordinate squared for the harmonic oscillator. And secondly, the indices were different. Here it was, for the hydrogen atom, it's k minus 1, and here it's k. And more importantly, the superscript was a half integer if it was the harmonic oscillator, but it's an integer if it's the hydrogen atom. So it's the same class of functions that are appearing, but actually they're completely different polynomials. Okay, but they at least they satisfy the same master formula here that tells you how to compute them. All right. So those are the polynomials that appear. And now you can put sort of everything together and write down the normalized wave functions. Now we're going to figure out what the normalization constant has to be, or at least I'm going to tell you what it is. It's kind of tedious to actually work it out, so we won't do that. But we'll do some checks. Okay, and so here it is, the wave function as a function of spherical coordinates, labeled here by the complete set of commuting observable quantum numbers. This is for the Hamiltonian, that's for L squared, that's for L sub z. Okay, this is equal to a normalization constant that I'm going to tell you what it is in a minute, times a factor e to the minus rho, times a factor 2 rho to the nth power, times the factor from the associated Laguerre polynomials, n minus L minus 1, superscript 2L plus 1. That's a function of 2 rho. And finally, the usual spherical harmonics. Okay, and now finally to tell you what the normalization constant is, it turns out to be 2 over n squared, Bohr radius to the 3/2, times the square root of n minus L minus 1 factorial divided by n plus L factorial. So why is that what it is? It's chosen to make the following be true, that if I do an integral over all r with an r squared factor, and an integral over all phi, and an integral over all cosine theta. Sometimes this is just written as integral d omega. That's just code for the same thing. Okay, multiplied by the wave function squared. Okay, that's completeness. And so the normalization is chosen to come out to 1. And that's the whole reason why this weird expression for the coefficient in front of it is chosen the way it is. Okay, any questions so far? Okay, so let's do a few of them just to see what they look like, and also because the lowest few tend to be the most useful. So we're going to actually do this just for z equals 1. And then at the end, I'll tell you how to get general z if you really need it. But we'll just do z equals 1. So this is the real hydrogen atom. Then when you plug into this formula here, okay, the ground state wave function is just 1 over the square root of pi Bohr radius cubed times the exponential, e to the minus r over the Bohr radius. So what happened there was the Laguerre polynomial was just a constant, and it gets multiplied by this other constant. And then the factor of 1 over the square root of pi is coming from the spherical harmonic. So note, this is proportional to the 0, 0 spherical harmonic, which is just 1 over the square root of 4 pi. And so everything that I'm about to write down is going to have 1 over square roots of pi in it. And the reason or the origin of the 1 over square roots of pi is always from the spherical harmonic. That's how it sneaks in. Okay, so that was for the ground state. And then for the n equals 2 level, there's a wave function psi 2, 0, 0, which turns out to be 1 over the square root of 4 times square root of 2 pi a0 cubed. The polynomial is 2 minus r over a0. And the exponential is e to the minus r over 2 a0. So notice the thing in the exponential changes when you change your n level. That was different from the harmonic oscillator where the exponential, first of all, went like r squared, but also it was the same exponential every time. Now the exponentials are changing, and note this is proportional to, again, y 0, 0. Okay, and the reason we know that is because these are psi NLMs, and so when we look at the last two indices, that's telling us what spherical harmonic to put. Okay, and similarly, psi 210 turns out to be 1 over 4 square root of 2 pi Bohr radius cubed, r over a0, e to the minus r over 2a0 times cosine theta. That's proportional to y10. Y10 is proportional to cosine theta. And then there's psi 2, 1 plus or minus 1. Those are equal to minus over plus 1 over 8 square root of pi a0 cubed, r over a0. Here the exponential factor is always determined just by the n, and then the angular part is coming from the spherical harmonics. So note this is proportional to y plus 1 plus or minus 1. Okay, and notice, by the way, these always have a 1 over the square root of a0 cubed, because wave functions always have dimension of 1 over distance to the 3/2. That's because when you do a volume integral of it, it has to give 1 when they're normalized. Okay, so that was n equals 2. And then you can similarly do n equals 3. I think there's more of these in the notes, but I'm not going to do these all day. So psi 300, just to give you an idea, looks like this. 1 over 81 square root 3 pi a0 cubed. And the polynomial happens to be 27 minus 18r over a0 plus 2 times r over a0 squared. And the exponential is different, e to the minus r over 3a0. Okay, and so one can continue doing this. And now, if you want the z back for z not equal to 1, so I'd set z equal to 1 when I wrote all those things. All you do is you take your Bohr radius and you replace it by the same Bohr radius divided by z. This is telling you that these atoms are getting smaller as z is getting larger. And that's because the nucleus is more attractive, so it's dragging the electron closer to it. And the closer it gets, the smaller the atom gets. Okay, so now one can sketch what some of these look like. Sketch of radial wave functions. So now I'm not including the YLMs in here. I'm just going to be sketching, for example, as a function of r, what r and L's are as a function of r. And so a special point is the Bohr radius, and here's twice the Bohr radius, etc. And so if I look at the ground state, it's just this exponential, which is starting here and dying off like, of course my pen wants it to be a straight line when I don't want it to be. It's an exponential decreasing like that. So this line is n equals 1, L equals 0, and therefore k equals 1. And notice that the number of zeros is k minus 1, so this thing has no zeros. It's just an exponentially declining function. So that's what the ground state looks like for hydrogen. And now we can graph similarly what the excited states look like. So let's do the n equals 2 ones. Okay, and again, we're going to pick off special values like a0 and 2a0. And out here somewhere is 4a0. Okay, and so the L equals 0 state is decaying like an exponential, but it's multiplied by a polynomial that has 1, 0. And the 0 turns out to be close to, but below 2a0. So it looks something like that. Okay, so this is the n equals 2, L equals 0, therefore k equals 2. And that has 1, 0. Okay, so number of zeros of the function is equal to k minus 1. Okay, and then there's the other n equals 2 state, which has L equals 1. And if we go back to the wave function here, somewhere up here, we notice that if L is non-zero, then there's this factor that's killing it near the origin. Okay, so that has a 0 at here and no other zeros. So it does something like this. Okay, this is the one for n equals 2, L equals 1, k equals 1, and so it has no zeros. When we're counting zeros, the origin doesn't count, and infinity doesn't count. Okay, and then similarly, you can do the n equals 3 level. At n equals 3, these wave functions get more spread out. So here's a0 and 2a0, and up here somewhere is 7a0. That's a special point, it turns out, because there's going to be a 0 close to that. Let's erase this and make a longer line. Okay, and somewhere up here is, not necessarily to scale, is 11a0. Okay, and so first of all, the L equals 0 state starts at a constant value here. And it sort of decays, has its first 0 there, has its second 0 at around above 7, and then it settles down to 0 again. So this is the n equals 3, L equals 0. Therefore, k equals 3, and therefore it has 2 zeros. That's what that wave function looks like. All the other wave functions at the n equals 3 level have L larger than 0, and so they all start at 0. Okay, and so one of them looks like this. They're all eventually exponentially decaying. This is n equals 3, L equals 1, k equals 2, and therefore 1, 0, not counting the one at the origin. Okay, and then finally there's the k equals 1, which has 0 zeros, and so it just rises and then falls down to 0. So this is n equals 3, L equals 2, k equals 1, no zeros. So by the way, the reason the 0 at the origin doesn't count is because that didn't come from the associated Laguerre polynomial. That came, going back up to here, the associated Laguerre polynomial is how we count the zeros. The one at the origin is coming from this factor. And so when we count zeros in this way and say that it's equal to k minus 1, that's why it doesn't count. Okay, so other things one can do is, in general, we'll prove this later, you can compute the expectation value of the radial coordinate. And this turns out to be the Bohr radius times 1/2 3n squared minus L times L plus 1. So one thing is it only depends on n and L. It doesn't depend on m. Another way of writing this is a0 times 1/2 3k plus L squared minus L times L plus 1. Okay, which I could rewrite as a0 times 1/2 3k squared plus 6k minus 1 times L plus 2L squared. So these are all the same thing, of course, but they have different applications depending on which thing you're going to hold fixed. So what is this expectation value telling us? If we interpret the expectation value as the size of the hydrogen atom, then the following things are true. First of all, it grows with n. So higher energy states are more spread out. It also grows with larger L for fixed K. So if you imagine holding the radial part fixed, the number of zeros fixed, then the faster the hydrogen atom is sort of rotating, then the larger it is. But you notice that if you wrote it in this way, with fixed n, then the opposite is true. So it shrinks with larger L for fixed n. So one way of thinking about that is if you're fixing n, you're fixing the energy. And then if it's got larger angular momentum, then to compensate for that, to have the same fixed energy, it has to be closer to the nucleus. Okay, and then finally, the size of the atom shrinks with larger z. And remember, that's because in all the equations, the Bohr radius is included in the form Bohr radius divided by z. So it just gets smaller as z gets larger. Okay, questions on that? All right, so I just sort of picked the normalization factor out of thin air without telling you where it came from, but let's just do some checks to make sure that we got it right. So we'll do some checking of normalizations. Okay, and we'll start, of course, with the ground state. The ground state is the n equals 1 state. And so if we check normalization, we're computing this inner product of the ground state with itself. And in position space, by completeness, we do an integral over all r, with the r squared factor included, an integral over all phi, an integral over cosine theta. Okay, and when we do, what we're doing is we're inserting a complete set of states, r, theta, and phi. Okay, but that's just the wave function squared, psi 1, 0, 0 squared, which we said was 1 over pi Bohr radius cubed times e to the minus 2r over Bohr radius. Okay, nothing there depends on theta and phi. So this factor is just going to become 2 pi times 2. So the whole thing is just 4 pi divided by pi Bohr radius cubed times this integral, 0 to infinity r squared e to the minus 2r over Bohr radius dr. Okay, and then we can do that. You can plug that in, but let's see how we do it really. U is equal to 2r over a naught is a good change of variables. And then r is equal to Bohr radius u over 2. And dr is equal to Bohr radius over 2 du. And so the whole thing works out to be 4 over, the pi's cancel, 4 over Bohr radius cubed The change of variables gives us 3 factors of Bohr radius over 2 cubed. And then what's left is the integral from 0 to infinity, u squared e to the minus u du. That integral is equal to 2. Okay, and so the whole thing equals 1 as promised. Okay, let's do one more. So we could do the normalization of the state 2, 1, 1, just to see how it goes. So we have the same integrals over r, theta, and phi. Okay, and then we have the wave function squared. That's exactly the same thing really as here. It's just we're replacing 1, 0, 0 by 2, 1, 1. And so let me just write that as normalization constant times r over a0, e to the minus r over 2a0, and then the YLMs give sine theta e to the I phi. Okay, now the e to the I phi doesn't matter because we're taking the square of the absolute value. So that's just going to go away because it's just a phase. And this constant is what we're going to find. We're pretending we hadn't already written down what it is. Okay, and so this is just going to give a factor of 2 pi. And so we've got 2 pi magnitude of c squared, integral 0 to infinity. There's an r squared here, and there's an r here, which is getting squared. So this is dr, there's r to the 4th over a0 squared. There's an e to the minus r over a0. It was over 2a0, but then we squared it. Okay, and then what's left is the cosine theta integral, which is minus 1 to 1 d cosine theta of sine squared theta, which is not hard to do if you change that into 1 minus cosine squared theta. Okay, then this whole integral comes out to be 4/3. This integral turns out to be Bohr radius cubed times 4 factorial, which is 24 Bohr radius cubed. And so when you multiply everything out, this is 64 pi Bohr radius cubed magnitude of c squared. And that's how you get that the constant is 1 over 8 square root of pi Bohr radius cubed. Okay, and you can never actually determine the phase of one of these wave functions this way. So we're just choosing it to be positive, which is a valid choice. Okay, so important things to remember in doing these, because they're common mistakes, are don't forget the r squared, and don't forget that things tend to have cosine theta dependence, which is non-trivial here. But for the YLMs, because they always go like e to the I phi times some power, and then you're taking the absolute square of it, this factor usually just comes out to be 2 pi, or basically always comes out to be 2 pi in these examples.
Professor?
Yes.
So if I want to calculate the probability, would I have to square that inner product?
Yes, that's exactly right. So if you wanted to calculate, well, here we're just calculating the inner product of a state with itself to find the norm. Okay. So you would replace this by whatever is your state, and then you would square it. Right? But here what we're doing is we're requiring that these things be 1. So I should have maybe written that here. Okay, these things are always supposed to be 1 if the thing is normalized correctly.
So when I square, because I remember in the probability we had that density function which was already squared. So would I square the result in the end result of the integral in the end as well?
Okay, so let's just write down what it is. So if you're in a state that we're going to call psi, then the probability of being in a state, let's say NLM, is equal to NLM psi, that inner product, magnitude squared. Okay, and this just comes from the postulates of quantum mechanics. But that's, so right here, we're not really calculating probabilities. We're calculating the norms of states, and we're requiring them to be equal to 1. And that's just telling us what the constant is. That's a prerequisite to doing a calculation like this. Because to do a calculation like this, I need to know what the normalization of this is. Okay, but in any case, this is equal to the absolute value of integral 0 to infinity r squared dr, 0 to 2 pi d phi, negative 1 to 1 d cos theta, of our wave function for the state. In principle, this should be complex conjugated. And then times the wave function that we're given here. I should have written R here. Okay, so this is the given state. And these are the energy eigenstates that we worked out. Okay, and then the whole thing gets magnitude squared. All right, so we're over time, but next time we will ask more questions about these states. In particular, we'll want to know for later use, what is the expectation value, my handwriting is deteriorating fast, of the radial coordinate to the nth power for any n. Okay, and so we'll do that next time. All right, so you have homework which is delayed due today. There is a new homework set out, which is due, what did I make it, a week from tomorrow? And then, so that's already out and should be findable on the course webpage. And then there will be one more shorter homework set after that, which will come out at some point. Good. Any other questions on today's lecture before I stop the recording? All right.